network could handle a bunch of much more complicated functions, but the bads are that the neural network itself ends up a bit more complicated, and you can potentially end up in some training difficulties a bit later, but let's save those problems for another day. Let's look at how these things work and look at this problem in particular. So data like this is not that hard to come across. Here's an example of data. This is the inverse sine function, arc sine. So you've got the x-axis down here, the y-axis here. I just took a sine function and flipped it 90 degrees. So for every x input, we're going to ask a neural network to predict the y output. And you can see at this point it's got 1, 2, 3, 4, 5 different options. So we're going to take two approaches. We're going to try predicting this with a standard neural network using mean squared error, and we're going to try it with a mixture density network. Let's see if this works. Sine prediction. Cool. Okay, we'll see. I'm just going to start loading in all my my imports. All my TensorFlow stuff has gone a bit strange recently since the new version of TensorFlow came out. I'm not sure how to fix it completely, but I think this will still work. So here's generating my data. You can see all I did was generate some random data on the y-axis using this NumPy's uniform random function, and then I took the sine of each of those bits of data to get the x-axis part. So now we get this inverse sine relationship between x and y. And there's a little bit of noise added to this just so that it's like not too easy a problem. Now we're going to try to fit this with an MSE. Basically, this example is taken straight from Bishop's paper, so it's not like I invented this. Lots of other people on the internet have given this, but I'm giving it to you today. So we're going to try to fit this with a typical feed-forward neural network. This is going to be, I guess, as standard as I could think of. It's going to be 2 hidden layers of hyperbolic tan activated dense layers in Keras. Those are these ones here, 1, 2. And then the final layer, the output layer, will be one single neuron, you see dense 1, and the activation there is going to be linear, just so we get the predicting any real value. This is going to be compiled with the loss value mean squared error. That's just basically the Euclidean distance between the x's and y's, or more or less related to that. And then the optimizer is RMS prop, and then we're going to fit this with the x data and the y data. 200 epochs. This is a very small network. It only has 15 units in each layer, so it should fit quickly. Let's do it. Okay, it's got 286 parameters. Oh, too far. Okay, so it's fit now, 200 layers. Now let's see what the loss value was over time. So I think the loss value is the orange one, validation loss is the blue one. So it came down to about, the validation loss is a bit smaller. Came down to this value about 20 and then stuck there, didn't move. So let's see the kind of predictions it makes. So I'm taking a bunch of test samples from the x-axis, and then I'm going to predict the y values for all those tests, and then we're going to plot it to see how well it does. Okay, is this a good match to our function? No, it is not. It's a bad match. So with this single output and MSE, you can see that it's kind of good at this end where there's no other branches of the function, and it's kind of good at this end where there's none. And it's okay in the middle where the mean of the function happens to overlap with that particular data point, but everywhere else it's pretty bad. So that's a bad outcome. Now, we can solve this. We're going to use an MDN model. So, first of all, I'm going to cheat and use my Keras special source MDN layer. This one here, mdn.mdn. And I have to give it, later on I'll show you exactly how this works. this has one output node. I just want to detect one value. And it's got one parameter, which is the number of mixture components I want. So the number of mixture components is a hyperparameter when you're dealing with mixture density networks. You can, of course, have many mixture parameters, but of course that expands the number of parameters in your neural network, and it might be better to have as few as possible. So I've chosen 5 here because I would like this network to be like exactly fitting the function. If I go for more, it might have not worked very well. So I'll start that. Now you can see I've got more parameters than before, 510 parameters. Basically because I've got this extra layer with 200 parameters. And now I'm going to fit this to the same data. Hopefully it works. I've run this example a lot of times, and I know that it's worked if it gets below 1.5 or around 1.5 on the loss. If it doesn't get there, it's not so good. So. Oh, it'll make it. Okay, so I've done my training now, 400 epochs. That was fast. You can do neural networks with slow computers. The validation loss and the main training loss are kind of equivalent, so that's good. It seems like the validation should be, the network should be okay. Now, the funny thing with mixed density networks is that they don't actually output your predicted values, right? We want this network to take X as input and give us Y, and instead of that, it's taking X as input and then giving us a whole lot of pi's, a whole lot of mu's, and a whole lot of sigmas. So we can't just take the output values of this neural network and apply them directly. We have to build some kind of function that constructs a mixture density model and then samples from it randomly to give us the output functions we want. I've got a little bit of information about how to do that, but we get our output tensor basically, split it up into mu's, sigmas, and pi's, and then I've got some other secret function called sample from categorical, which gives us the component we want to sample from based on those pi's, and then, oops, then I construct this, then I construct a normal model using NumPy, the NumPy library, to sample from a single model that I know I need to sample from and return the sample. So I'll talk a little bit more about that in a minute, but you just have to bear with me that you need to use this function and it ends up being a little bit more complicated. So that's the downside of these models. But I can still use it. I'm doing the same test, testing 300 samples. Let's plot the predictions. Okay. That's much better, isn't it? So you can see that sometimes the MDN gets it a little bit wrong, right? Because we're sampling from a probability distribution. It's got a little bit more flexibility. If you sample 1,000 times, you might 1 in 1,000 times get quite an unlikely sample pulled from that distribution. But we can investigate a little bit more about what's going on here. I told you it's giving these values outright. So what I'm going to show you is a plot of all of the means. So for each value of X, I can plot the mean at that particular value, and that is quite interesting. The mu. Yeah, this is cool. So you can see that I've got 1, 2, 3, 4, 5 means. 5 means for each input value. Each X outputs 5 different means, and the neural network has learned to place those means in somewhere in the network that's useful, right? And you can see it's made a bit of an unfortunate mistake here. It's got 2 means dedicated to this lower branch of the function, and up here it's got no means dedicated to it. So if only it had moved one of those means to that part, it would have had a better result. But this is like a training thing. There's some stochasticity in the way that neural networks trains, and if it just happens to get that one in place, it does a better job. But you can see that the means basically follow each branch of this function pretty well, except for these ones which kick out because they're trying to predict these values in here. So that's a bit unfortunate. But one more example, I think I've got the means here. Yeah, I've got the means multiplied by their standard deviation and pi. So we can, I don't know why I've got standard deviation there, but just the pi is what I really want. So this shows us the means and the weighting of each mean at different parts of the plot. So, it's annoyingly one's red, but we can see this green one is most weighted towards down here, and the purple one's sort of important. Then the orange one becomes prominent up here, then the red one, then the blue one up there. So each of those means is sort of responsible for, each of these components is responsible for predicting a different part of this plot. So that is kind of cool. MDNs, plotters, predicting this difficult function. That's my examples here. I might add another comment that I've got to talk about. That was my 4 results. This is my MDN architecture. Oh yeah, I didn't mention the loss function. I'll talk about that in a little bit. There's my correct result. This one was in that training run I did much better. It covered it almost precisely. Pretty cool. Okay, now we're going to get inside this layer. So we've got 5 minutes left really. So I told you that I used this like secret source MDN implementation because I've got my own implementation in Keras. The reason I did that is because I wanted to have like the best MDN I could make. It has some secret features like you can predict not just one value from these normal distributions, but have multivariate normal distributions, which is cool. You can predict lots of values at once. And it works for RNNs, it works in data that has like time distributed. So if you've got a sequence of multi-valued real value vectors to predict, it can handle that. But if we don't want all those special features, it's not that hard to just code up an MDN in Keras using the functional API by yourself. So I'm just going to read this along with us. We start out with our input layer. Has anyone used the functional API in Keras before? Hands up. There's a few nods. 2 nods. Does anyone use the sequential API in Keras? More nods. Does someone not know what I'm talking about when I say Keras? What is Keras? Keras is this deep learning library, right? Everyone knows what Keras is, right? Keras. Yeah. Well, there's 2 different ways to write up networks in Keras, right? There's the sequential API where you like say, okay, add a layer, add a layer, add a layer, because you've just got a sequence of layers. That's like the easy mode for Keras. And then there's the functional API which is good for situations where you might be branching out into multiple layers and you don't want them to be exactly one in front of the other. And for MDNs, that's what I've got to do. You'll see why in a minute. So I've got a function up here. I'm not going to worry about that for the moment, but my input layer, just one input for the X. Hidden layer is a dense layer, another hidden layer, dense layer, right? We're not doing anything special so far. And then this is where I'm doing the branching. I've got 3 dense layers, and they all depend on the previous hidden layer, hidden 2, hidden 2, hidden 2. This one's going to be my mu's, this one's going to be my sigmas, this one's going to be my pi's. This is not too hard, is it? All I'm doing is just making a dense layer for each kind of parameter that I want to predict. The reason that I separate them out this way is because some of them have to have special activations. The sigmas, we don't want our sigmas to be less than 0, right? Because that doesn't make sense to have a standard deviation less than 0. Actually, I don't want them to be even close to 0, because when you have a standard deviation very close to 0, your normal model starts to get very, very high. Actually, it goes way past 1 and goes to infinity, the limit of the normal model. As the standard deviation approaches 0 is infinity. So if we had a standard deviation of 0, we would have a bad problem with training our MDN, so we don't want that. That's why I've used this special activation function here. It's the ELU, I think that's the exponential linear unit. It's sort of exponential on the left-hand side, on the negative x-axis, and then it's linear on the right-hand side. People say on the internet that that's the best unit to use for sigmas in neural networks. You know the way these things go with deep learning. It's like rumor has it. Someone says on Twitter. Jan LeCun says one day, use ELUs for your MDNs, and then everyone believes it. This is just how deep learning is at the moment, but I've got a citation for a reason to use that, but I'm not quite sure. What I am sure about is I really do want to have this small offset here so that it can't go below 0. Then I've got my pi's, which don't need an activation. They're just the logits, the sort of unsoftmaxed categorical distribution. And then the final part, I've got this concatenation layer, which just puts them all in a list. And the reason I do that is because I just want to have those be able to be compatible with the sequential model, where I'm sort of pretending to have one input and one output, whereas in fact I've got one input and 3 outputs. But if I concatenate them all up here, it just makes things life easier later. So then I build my model with the inputs, outputs is the MDN out. That is the list of all of these parameters smushed together. And that's my MDN layer, right? Easy. Well, the hard part, unfortunately, the hard part is the loss function. Because in the loss function, we need to find a function which will give us the negative log likelihood. You've heard that word before from deep learning courses, negative log likelihood of the predicted value, of the true value compared to the predicted value. So the predicted value is this parameters of this mixture model, and the true value is the number we would like to draw from that model. So we have to construct the PDF, probability density function, of this mixture model using those components and then see what the log likelihood of drawing y true is from it. So that's a little bit of code. I'll just go through it over 3 quick slides, then we'll be done. First things first, we have to extract the mixture parameters. So to do this, I just use TensorFlow's split operation. In this case, I'm splitting it back up into 3 groups of the number of components. Then I have to do a bit more splitting, because unfortunately you can't iterate over a tensor in TensorFlow or Keras. Yeah, that's not so bad. Next part, I have to construct my mixture model. Now in TensorFlow, there's a library called TensorFlow Probability, and in fact a sub-library called TensorFlow Probability Distributions, and I can get out of that library a mixture model, which is great. And the mixture model is made of 2 things. It's made of the categorical model that I talked to you about before, and a list of the components, so one probability model for each of those components. So I make my categorical model, again using TensorFlow distributions, takes the out pi's as its parameters. Then for each mu and sigma in my lists, I'm making a normal model. Log equals log. Log is sort of another word for mean in these models. Scale is another word for standard deviation. Then I construct my mixture model with the categorical model and a list of the components. That's not too hard. You can do this from first principles. In some of my earlier MDN work, and a lot of the ones you find on the internet, people are sort of typing out that PDF for the normal model, you know, the really ugly function I showed you before, typing it all into TensorFlow. I say, if the abstraction is there in the library, why don't you just use it, right? Then it's someone at Google's problem to make sure it's right. Yeah. They should be able to handle it. Now the last part of my loss function is to actually calculate the likelihood. So I've got my mixture model, and then I'm going to find the log probability of drawing y true from that log model. Then I just have to put a minus sign in front of it and get the mean, and that gives me my loss value. Yeah, so that's not too hard. It looks a little bit difficult from a distance, but each part is quite manageable. Now, in my last minute, I might give you a preview of what I'm going to do next time. Next time I'm going to talk about MDNs even more. I'm going to talk about RNNs. And my next time is not until after the break, in the next lecture week. So this version of the mixture model I just showed you works well for one-dimensional distributions, but you can have a 2-dimensional normal model, right? This one's got 2 dimensions. You can actually have n-dimensional normal models, multivariate normal distributions. And our MDN supports that, so it's not too hard to extend it, given that we've got these cool TensorFlow distribution libraries. If you're interested in more work about that, have a look at the code from my Keras layout. And then we might want to use these things in RNNs, right? In some situation, for instance, when a robot has to decide where it's going to move, you might model that as multiple different sort of 2D distributions, right? Different locations in space where it moves together. And people have used these in different problems like handwriting generation, not recognizing handwriting, but actually writing. You can do this by sort of predicting where a pen is going to move next in 2D space. And you can see that here's the mixture model likelihood function sort of overlapped here. When this person has written, or the neural network has written a U, and then when it has to jump up to the start of the M, it's got a very wide distribution, right? Because it doesn't know where it's going to go. So it eventually picks to move to the start of that M. That's some work by Graves from 2013. Some other things, you can use this for sort of artistic purposes like generating kanji or doing human-based sketches. This is sketch RNN, which is a variational autoencoder using an MDM. That's some work of David Hart. We can use this in a mobile app. This is some work from me, RoboJam, which uses an MDM to reply to a musical performance made on a touch screen. So that's similar to doing handwriting right, except it has an extra dimension of time. You need to have the rhythm of the taps on the screen correct as well as their location. And then the final thing, which is quite recent work, which I find quite interesting, is this idea of a world model. So these guys, David Hart and Schmidhuber, the legendary Schmidhuber from LSTM fame and many other accomplishments, have had a paper recently. I think it's at the conference, big conference NIPS this year, where they train a variational autoencoder for visual perception in a game environment. They're using VizDoom, the Doom environment. Then they're using an MDN to predict the next latent vector, sort of trying to predict into the future in this game. So you can use this MDN to help an agent learn to play this game, which is quite a cool idea, I think. Yeah, so now this, I've got a few references that you might be interested in if you're interested in following up on RNNs. This talk is on my website. I'll put a link on the notes. That's creditprediction.xyz. You'll find it if you want it. And I think now it's 3:19. That's the end of my talking time. I've blown through my talking time. Yeah, through 15. So.